Hello again, Mark here. This is a continuation of the NEET 21 Unit 3 and 4 exam. This is questions 11 to 20. Had a bit of a technical glitch before. I had to stop the file and save it at the end of question 10 instead of the end of question 20. So there are going to be two videos covering the multiple choice questions and another two videos covering the written answers. Okay, here's question 11. Progressive transverse wave. A progressive just means it's moving, okay? Transverse wave passes through point P, as shown. There's point P. The wave is traveling to the left, so it's going that way, arrowhead there. All right, so the wave is physically moving that way. For the instance shown in the diagram, the particle at point P is moving, and the answer is upwards. All right. If you imagine that this is a surfer, and he's beyond the breakers, and he's out in the waves in the ocean, and the ocean waves are going that way. As this wave passes beneath him, he's going to go up and then going to go down as that wave passes that way. All right. So it's definitely going up. In order for that point P to get over that wave, it's got to go up. All right. Fairly easy one. Question 12. This is a straight out knowledge question. It says, which one of the following correctly identifies two properties of a region of the magnetic spectrum? Just hold on a second. Right, just dialed up a light on this situation a little bit. All right. Question 12. Okay. Simple table, property 1, property 2, you have to find the row in which both of them are correct. Okay. X-rays are not the highest energy per photon, gamma rays are. Right, so it's not that. Gamma highest, yeah, that could be right. Second one, microwaves, less energy than infrared, yes they do. Right, they have less energy than infrared. Infrared is just before visual. Useful for communication, absolutely. Mobile phones run on microwaves. So that's the first one that's totally correct. If you want to go further and just check that the other two are definitely incorrect. Infrared, more energy than ultraviolet? No, ultraviolet has more energy than infrared. Gamma rays, this better be wrong. Useful for thermal imaging and heat mapping? No, they're not. Okay, so answers B. Question 13. Excuse me. Rightio, dispersion of a beam of white light through a triangular prism does this, makes a rainbow, right? It's caused by refraction. When it goes in, it bends towards the normal. There's the normal. Right. Normal is an imaginary line drawn at right angles to the surface. White light, or any light, going from air into glass, because glass has a higher refractive index, it's going to bend towards the normal. So instead of going that way, going straight, it bends a little deeper. On the way out, it bends away from the normal, but because the surface is in a different orientation, that's the normal now. And so instead of going out that way, it's bending away from the normal, right? And the upshot of that is that it actually bends in the same direction twice, splits into its colors, we get a rainbow. All right, which one of the following statements about dispersion through the prism is correct? All right, the refractive index of the prism is greater for high frequency colors, yes, right? The refractive index for any material is dependent on the frequency of the light that's going through it. Right? Different frequencies of light are more or less affected by it. Higher frequency means you bend a little bit more, you refract a little bit more, and that's why violet gets a really strong curve and red doesn't bend as much, and that's why you get a rainbow. There you go. So A. Question 14. Polarization. Aha. This is something I haven't seen for a while. Polarization of visible light occurs when a property of light waves oscillating in various planes is affected. Which of these clearly identifies this property, its amplitude? I just want to remind you what polarization is. Okay, so I'm just going to zoom this out for a minute. Okay, here's a wave. There's a light wave going that way. If you could see that thing coming towards you, if you were actually right here, looking at it and looking better than that, this from that perspective would look like this. It would just look like up, down, up, down, up, down, up, down, right? Coming straight at you, right? However, they're not all vertical, of course, because light waves are made in all sort of higgledy-piggledy ways from electrons that are jumping in atoms, so they don't all come out with a top and a bottom and a top and a bottom. We draw them like that because it's convenient. But as well as coming at you this way with a top and a bottom, some of them are going to come in sideways. Some of them are going to come in like that. And in reality, this, if you could see all these light waves coming towards you, they would look like this. every now and then there is one that is actually vertical, but they're all over the joint, right? Polarization is the using of a grill like this, some sort of grill, and they're fairly easy to make. Sunglasses have got this, right? Polarization is, polarizing sunglasses. Polaroid sunglasses have got this. Is the use of a grill that actually blocks all of the waves that can't fit through the slots of the grill. So that one gets in, that one will get in, that one will get in, that one will get in. None of these guys will get in. Nothing else will go. So instead of getting like 20 of these light waves going through, you're only going to get 4 of them, right? And the light that comes through is now all oriented like this one. It definitely has a top and a bottom, and the plane in which it vibrates things is vertical, right? And that particular light, collectively, those 4 photons have been polarized, right? They're all going in the same orientation. So that's polarized light. Okay, question 15. This is worth a bit of a diagram. This is a very utterly simplified diagram of what's actually on the question book. It says Wally is in a car, Jenny is standing on the side of the road, and David is in a truck. David's going that way, Wally's going that way, Jenny's standing still. David sounds his horn. Now, I've got a reproduction of David here. So I'm just going to do some D's. So if David's truck was not moving at all, and he sounded his horn, let's just say that this is stationary, right? Velocity equals 0. And he sounds his horn. Waves of sound would come out this way, and waves of sound would come out that way. And the wavelength on that side and the wavelength on that side would be the same length. Right? Makes complete sense. And somebody over here and somebody over here would hear the same pitch of sound. If there was Jenny and Janice, they would hear the same pitch of sound. If David is moving, it's a slightly different story, because if this truck is suddenly going that way, he's catching up, not quite, but he's getting closer to these waves. So once that wave has been traveling to there, David's truck is actually closer when it releases the next wave. And so the gap between the waves in front of the truck is less. So it's going to look a bit like this. And because he's going away from these ones, right, as the wave is going that way, the truck is going that way, so the gap between the waves is more behind him. So it's going to look like this. So that's how the waves go. Right? This is called the Doppler effect, and it makes the horn sound higher than it really is there and lower than it really is there. Short wave, high frequency, high pitch, right? Long wave, low frequency, low pitch. Right? So both of these, the short answer to this question, the question is basically saying, how do these people hear the horn, right? So what is really happening is that because David's truck is moving, they're coming out at a higher pitch anyway, straight away. And these guys are coming out lower, but that doesn't matter. This is happening up here, right? So David is traveling with the horn, right? So he hears the horn as it really is, right? The horn is moving at 50 kilometers an hour, and David is moving just behind the horn at 50 kilometers an hour. So it's as if the horn and him are stationary. So he hears it in reality as it really is. He hears it like that, right? Because it's moving, but so is he. Excuse me. Jennifer is going to hear it at a higher pitch than David. And because Wally is traveling this way, he is actually hearing these things at an even higher pitch, because when they get to him, there you go. If Wally was standing still like Jennifer, Wally and Jennifer would hear the same pitch of sound, but Wally is actually going fast, so he hears that one and then that one and that one and that one faster. He gets through, or those 4 waves get through his ears faster than these 4 waves are going to get through Jenny's ears, because Wally's actually catching up to them. He's meeting them halfway. Right? So in terms of who's hearing which pitch, David is going to hear the true pitch. Jenny is going to hear a higher pitch. And Wally is going to hear the highest pitch of all. One of the answers of that question says that. And it's actually option D. It says, Wally hears a higher frequency than Jenny, right? All of the other options are incorrect, right? That's the reality of what's actually going on. Thought it was worth a diagram, that one. Question 16, sound waves are passed through a gap as shown, and you get diffraction. Okay, seen that 100 times. The sound waves are a frequency F and the gap is width D. Which one of the following sets of values for F and D are going to lead to the greatest diffraction occurring? Okay, the trick is when this ratio is closest to 1, you're going to get the best diffraction. Typically, the wave is way smaller than the gap, right? Which is why, like when sound waves go through a gap between two buildings, for example, you don't get much diffraction. You get some, right? But not much. Certainly when light waves go through a gap between two buildings or whatever, you almost get no diffraction whatsoever. But if the wavelength of whatever wave is roughly in the same power of 10 as the size of the gap, that's when you get maximum diffraction. So you basically have to find out which one has the closest, right? Now, these are not wavelengths, they are frequencies, and the wavelength equals 1 on frequency. I don't know why I didn't do that. So if you combine those, you get D divided by 1 on F, which means D times F, right? So they're proportional to D times F, right? Excuse me. So if D times F, if that times that comes closest to 1, you've got your answer. And the answer there happens to be A, right? If you do that for all 4 of them, you end up getting A being closest to 1. Question 17, this should be a reasonably easy one at the moment. Creation of helium nucleus in the sun can be modeled by a fusion of 4 protons. Right? Let M proton be the mass of 1 proton and M helium be the mass of a helium nucleus. The speed of light is c. Okay, which one of the following represents the energy released in the production of a helium atom in the sun? Okay, so this is from E equals mc squared, right? So they've all got c squared. So the question is, what's the m? That's all they're asking you for. And the m is the mass defect. 4 protons separately will weigh a little bit more than 4 protons crammed together to make a helium atom, right? And that difference in mass, that tiny little difference in mass, is where this energy comes from to hold the whole thing together. And that's why nuclei of atoms are very, very well tightly held together, right? So what's the mass defect? The mass defect is that minus that, because this is the bigger one, right? The separate mass is larger than the joined together mass. So what you're looking for is m proton minus m helium times c squared. And one of those is going to say it. Sorry, 4 m proton, because we're joining 4 protons together, so it's actually C. There you go. This is another one that should be reasonably easy. One of the reasons it should be fairly easy is because we did this fairly recently, so it's not like you have to study something that you haven't seen since March. Okay, an electron goes through the gap. Right. This is the Heisenberg uncertainty principle we're dealing with here. Under certain conditions, the electron is able to diffract. Okay, so the uncertainty in the y position of the electron in the gap affects the uncertainty in the y direction of momentum only, right? Heisenberg's uncertainty principle says that you can't be completely certain about something's position and its momentum at the same time. Now, if this gap is wide, then as this thing is going through the gap, and all you know is it's going through the gap, you don't know whether it's there or there or there or there or there, right? So the uncertainty in its position is high. But because the gap is wide, it's almost certainly not going to diffract. So the uncertainty in its momentum is low, because you know it's almost certainly going to go straight ahead. Only the ones that just miss are going to do a bit of diffracting along the edge. If you close the gap, or nearly close the gap, then when that electron goes through the gap, there is very little uncertainty about its position. It's got to go through that tight little hole. It's going to be there. Right? But because its wavelength, its de Broglie wavelength, is now roughly the same size as, or closer to being roughly the same size as the gap, right? It's going to diffract more. So you're more certain about where it is, but you're less certain about where it's going to go, right? That's Heisenberg's uncertainty principle, right? So changing the uncertainty in the y direction of one of those things changes the uncertainty in the y direction of the other one of those things in the other direction. One gets more certain, the other one gets less, but they're both in the same direction. 19. This is just a straight out knowledge question. Which one of the following instruments is responsible for the production of light by the forced circular motion of high-speed electrons? One of those, synchrotron. Right? Should know how each of those four create light. Right? Okay, question 20. Pardon me. Right. A correctly calibrated data logger. Correctly calibrated, as soon as I see that, that tells me that it can't produce a systematic error. Right? If it's correctly calibrated, it's working properly. Determines that the frequency of a note from a guitar string is 440 hertz. So we're pretty damn certain that that's right. Okay. A group of students using the same guitar string to record the note on a different data logger get these results. Right? They do it 5 times. 1, 2, 3, 5. Yep. They get these results. The data is, okay, we've got to decide whether it's reliable or valid. Okay. If it's valid, it's close to that, right? 451, 450, 452, 451, 452, it's nowhere near that, right? There's a pretty significant error, right? So the correctly calibrated data logger gets it right. This one has probably been incorrectly calibrated. It looks like it's off by about 10 or 11 or 12 each time, right? So it's not valid. It is reliable. The error is plus or minus 2, and all of these are within 2 of each other, right? So one sort of question that I ask about reliability is, looking at those, could I have a stab at predicting what the next number would be? Right? And it's either going to be 450 or 451 or 452. So I've got a fair chance of guessing it. Right? That's pretty predictable. Right? So it is reliable, but it's not valid. So it's going to be C. There you go. Okay, that's the end of this. Excuse me. That's the end of this video and the end of the multiple choice questions for the 2021 NEEP exam.